three quadrilateral face and two triangles. Okay, so five faces, very strange shape. But this is element for parallelohedron. So you can construct. There are 5 different family of parallelohedron, and here this is elongated rhombic dodecahedron. And if you like to make, for example, rhombic dodecahedron, if you like to make, then you delete this part, okay, this part, and put them together. This is rhombic dodecahedron. So this was box, okay, rhombic dodecahedron. And if you like to make cube is also a space filling solid. Okay, so if you remove this part, okay, this part, maybe you see, you have already seen cube. And can you see truncated octahedron? This pink truncated octahedron. You can see through the window here. If you remove this truncated octahedron, we can see. Ah! So, I have explained 3 notions. The type, and reversibility, and decomposability. And superficially, we think these 3 notions are altogether different. But in the underneath, it combines. It has a very strong connection among 3 notions. I will show you a little bit, but 28, so until 35, 40, until 40, so 10 minutes more, okay? So P1 type is a polygon which tiles a plane with translation only. So parallelogram and hexagon, parallel hexagon in 2 dimensions. And 3 dimensions, as I told you, few drop, 5 families. Okay, and this one tiles a space, and hexagonal cylinder also tile the space, and rhombic dodecahedron tiles a space, elongated rhombic dodecahedron tiles, and the final one is truncated octahedron. Okay, you see. So there are only 5, and so P2 tile is a polygon which tiles a plane by translation and 180-degree rotation only. Then the quite easy statement is this: every convex P2 tile belongs to one of the following 4 families. So by tiling theory, ancient tiling theory, there are every triangle tiles a plane, every quadrilateral tiles a plane, and exactly 14 different kind of pentagon tiles a plane. Maybe some of you ask me, I said exactly 14. Maybe some of you who are familiar with tiling theory says at least 14. But very recently, one of my colleagues, Sugimoto, proved there is no more no more 14. So proved. So only 14. Okay, and three different family of hexagon tiles plane. So from that we can derive this theorem quite easily. And but three-dimensional case, the problem seems to be easy. So three-dimensional P2 tile. That is convex polyhedra, each of which tiles a space, tessellates a space in P2 manner. P2 manner means translation and symmetric. 180 symmetric with respect to some axes. Okay? And this one I told you. And a net of convex polyhedra is defined connected planar object obtained by cutting the surface of P. I demonstrated there. And almost regular tetrahedron, I like to call it arc, is a tetrahedron with four congruent faces. And note that there are infinitely many arcs, because take any acute triangle, and along the middle line, dotted line, you fold. Then you will have a tetrahedron which has four congruent faces. Okay, so this is one of art. So from this one, you can make infinitely many different non-similar art. Okay, and so every net, convex or concave of an arc, almost regular tetrahedron tiles a plane in P2 manner. And since this blackboard does not work, so I will show you by CG. Here is regular tetrahedron. Okay? And you cut as you like, something like this, and something like this, and from the top, and open. And this figure will tile the plane in P2 manner. So first you rotate, okay, and by translation, okay. First this and this angle, and next up and down, okay, like this. Next one. Oh, it doesn't. Okay. So we can create many artwork like this. You can be like Escher, Maurice Escher, because repeated pattern. So no matter how you cut, that will tile the plane. So Maurice Escher salt and salt, and if he make this mountain, then here he must make valley, okay? Mountain valley, and so on. And but in this case, automatically you can. So this is also by applying the theorem, and this is iris. So this, for example, pink part, if you fold again appropriately, you can make regular tetrahedron. Okay? Because this is a development. This is a net of regular tetrahedron. And reversibility appear in nature very often. For example, in biology, box, a kind of green alga, known as one of the most simple colonial organisms, reproduces itself by reversing its interior offspring and its surface. So first the eggs are outside, but this green belt change and become, and finally the eggs are inside of green belt. Okay, so this is ball box, and many phase transition, FFC, phase center, the Voronoi diagram. Okay, and so if a pair of polygon A and B is reversible, then each of them tiles a plane by translation and 180-degree rotation only. So A and B, so with the same area. And is this reversible or not? That was the original question. So maybe you will think equidecomposability or Dieudonné, Andy Dieudonné's Haber-Dasher's puzzle. Okay, it's related. And so, for example, here is blue triangle, and I want to make red parallelogram with, of course, with the same area. Then I will dissect this along the red line and fix one part, and the remaining three pieces we rotate like this. Okay? Then blue triangle change to red parallelogram. And next, red parallelogram to blue triangle. Blue triangle to red parallelogram. And repeat. Then you will see two tilings. One by red parallelogram and the other by blue triangles. Okay? Very speedy, quickly it goes. So watch, please. So, do you see two tiling or superimposed? So, the reversibility is a tiling problem, actually. So, 2 minutes more. So, recently we proved this for an arbitrary convex P2 tile, P and arbitrary family F1, F2, F3, and F4 of a convex P2 tiles. There is a polygon Q, a member of F5, such that the pair P and Q is reversible. So this changes to this, and this hexagon changes to this square, and the canonical, the polyhedral is canonical if that is symmetric with respect to each orthogonal axis like this. And so this is rhombic dodecahedron, change it to truncated octahedron. And you will see that the tessellation by truncated octahedron, okay, and the other is just one, but box will tessellate the space and superimpose in your brain, in your mind, and they cut each other. Okay, so like this. So next one. This is rhombic dodecahedron and cuboid, like this. So superimposition will tell us how to dissect polyhedron to make reversible. Okay, and here is many examples. cube to hexagonal cylinder and so on. But let me pass this. Okay. And the final thing is this is pentadron, is a convex pentahedron whose net is as follows. This one, okay? And we can make tetrapack, and every parallelohedron can be built, constructed by copies of pentadron, cube, hexagonal prism, truncated octahedron, rhombic dodecahedron, elongated rhombic dodecahedron, like this. Okay, and so this is also derived from the reversibility. So thank you.